so the setup, we should also set up some system. It depends on the your availability. So if you have any Google account available, so if you have any Google account, so please raise your hand. Okay, so yeah, I think so. I uploaded on my slide on the Slack channel. So please download and see this page. And there are several links, and you can jump. You can jump. Click this link to the Google Collaborator. Yes, like this. I think you are, if you are a Google Colab user, how to run this script. So only push this play button. So yeah, we have such a result window after calculation. So this script returns our power methods, which computes the largest eigenvalue and the eigenvectors. So I prepared the 1, 2, 3 scripts, so you can jump either power method, QR iteration, and the last one. So it is the general eigenvalue solver driver routine. This is included in the very powerful Python the package. So the NumPy. It provides the linear algebra routine. In it, the eig. So it's calculates any eigen problems for even it is symmetric, non-symmetric limit and complex number matrix. Okay. Okay. So next one, if you don't have any Google account, so next one, if your laptop, your laptop's already installed the Python interpreter, so you can download this Python script from this the public box folder. But it is locked with the password, so please fill in the password unlocking. So once you download the zip file, then unzip, you will find 1, 2, 3 these script, Python script. Okay, so I didn't know the open on demand it has Jupyter's interpreters script interpreters mode. So still we have the two option to run the Python scripts on the Fugaku system. So, one method, I think you already have a Fugaku account and the availability to access the open demand. So here, I cannot see this. yeah, interactive application tab, and select Jupyter. This is a Jupyter Notes. Work small. You have to change this by any tag option. Oops. How to submit?
Just go to the bottom.
Words?
Just keep going down.
It's a bottom.
Pushing more down.
Okay.
There you go.
So I think that you find at the bottom this one. Okay, launch. Okay, push the launch button.
Don't delete it.
Okay. Don't delete.
Yeah,
So
just keep refreshing until
Okay.
it says you can start.
so wait a couple of minutes, or if you run already, so running.
Oh, that's also
one.
still delete.
I stopped the one and wait. It's a queuing. It's queued. So if queued session is sort of available, so your turn. So maybe so this status changed and pushed or something. So I think
you have to refresh it to see the.
refresh.
It doesn't automatically
Really?
change. Ah, see, starting.
Wait. Okay, starting.
Yeah, then refresh again.
Refresh. Okay. Yeah. So. Okay. So when your turn is coming. Okay. So start this connect to the Jupyter. So another window. It will open. Okay, like this. Then it's difficult to see which one.
Yeah, the one at the top one.
Yeah, top one.
Python 3.
Okay, so how to import the master? I don't know.
I don't know if you can. You want to upload the Python notebook to Fugaku. So if you go back to Open on Demand, there, and then you click on Passenger Apps. Passenger Apps. There you have the file system. So you launched into Home, so you want to go to Home.
Okay, I think the easiest way to open the terminal one. Okay, I should. Okay,
Yeah, but even from the terminal one, I don't know.
yeah, terminal is easy. Okay, so close. Okay, I try again. Delete and delete. Interactive. It's difficult to see. Jupyter launch. Just one more. Okay, so it takes time. So another option. So yes. On demand.
It works.
Oops. Is it working? It's just still cute. So open demand. Okay. So oops. Okay. So here is the shell access. So we will open the standard console terminal like this. Okay, so use the Python front end. So I put the sort of the Python script here, so you can copy this single file. It contains the sort of Python script and the setup shell script. So this is necessary. Here, this is my home directory. I made a ACM A0 2026 directory. We should copy also this file. Ball 0308 material science SC. Okay, so here this. Oops. Zip. So I copied the sort of all the files file from the common the shared directory. Then so I unzip like 3. It's difficult to malicious font size. But anyway, so 1, 2, 3 Python script and the setup sh so shell scripts are generated. So if you, I'm sorry, so this one side is too small. I don't know how can I enlarge. I'll try. Okay, maybe you can read this. Okay, so these files. Okay, so set up the loading the the software configuration. So run this setup the shell. So running the script source, put the space and set up the shell. Yeah, so it is going to set up the open source software repositories from the database and make it enables you to access Python, any Python script. Okay, so I think it's a lot. There are several warning, but so it is okay. So please check the Python 3 commands whether it works. Okay, so if you see there are this prompting, so Python's latest version, it works. Okay, so Python is enabled. So if you want to run the Python script, Python, then power. Okay, so Python script. Why? Okay, so you get the same similar results. Yes. Okay, so this is run on a Fugaku front-end system. Okay, so if we where did I put? This is not. If we run, okay, so Google Collaborator. I put additional comment to display the visual graph. But also the Python script on the Fugaku, so they are commented out. So if you have the Python or some visualization or the popping up or this display, additional display is enabled. So you can put not really plots or the additional or the packaging on your system. So yeah, comments. These are make this commented line they're available so you can run and it's you can draw the several these so convergence histories on the system. Okay, but also these results they should be almost similar to even we run the Google Cloud and the Google front end, so your laptop or Python interpreter system. Okay, so yeah.
I think that inside the zip that we copied, I'm not sure, but there is no setup script.
No.
Oops. Maybe there is something with the like we cannot copy or something like that.
Okay, I think I put the the older version. Which one? this. I copied the sort of setup script on the sort of same directory. Copy the sort of this script onto all your directory. Then run this source setup. So only one time. So if you run this script the second time, several times, so maybe it violates the sort of same setup for the configuration. Just only one time. Setup script, so it includes just only these three lines, so three commands, so very easy. But also some combination which affect the running some conflict reviews that happen. So I carefully chose the sort of this combination. So yeah, so this running this setup script, so it is easy to set up, easy to configure sort of this combination parameter system. Anyway, okay. So if you're ready for some difficulty to access your system, Gaku or Google Cloud or your local Python. No, if you don't. Okay, so suppose you don't have any issues, so I continue to explain the sort of the second step. Okay, so for PY, this is the Python script. So it includes the sort of several steps and the sort of function. The first function is just a normalization and the for method main. Okay. So this script includes the sort of the sub helper function and the sort of main function, so for method. So the main, okay, so last part from the sort of definition of the sort of matrix, input matrix itself. From here, and the second line, so lambda x history, it's there sort of the output from sort of power methods invokes the results. So power method with the sort of arguments to the matrix or array A, it computes the sort of the eigenvalue, largest eigenvalue with the sort of using the sort of power method. Okay, so going up to the sort of main part of the program. But you see the sort of the first 1, 2, 3, 4, 5, 6 lines. So they check the sort of arguments. So either matrix is a sort of a 2D array or a shape is a sort of squares style. Just only check, and then so x equal normalize or something like this. So this power method needs the initial guess. So randomly, so this method generates a sort of initial guess x0 by the uniform random number. Then here, so ax equal a at x at mark with the two array. So this is the matrix or matrix vector, the multiplication or the operation. So this is defined in the sort of NumPy package. So in this case, a at x, this is a general matrix vector multiplication. The ax, so it contains the sort of results, ax, a time, a and product of the matrix A and ax. Then we compute the next step. So the ax dot ax. So this is a sort of vector the product. So it's calculates the inner product. We need to compute the sort of the norm. So norm of the vector ax. So we compute the mass square root. Yes, ax at ax. Then so we normalize the ax and also the updates the vector x by the normalizes ax. But this is a sort of iterative method. We should check the sort of stopping criteria. So stopping criteria. So here the matrix matrix and so the vector product iteratively. So it's theoretically increase from the certain value to the maximum matrix eigenvalue. So it is always not uniformly increasing. But when it stagnates or the certain value, so we consider it is converged. So stopping criteria is the old previous the eigenvalue and also the current eigenvalue to be computed. So we compare the two numbers, and if the current value is smaller than the previous one, so we stop. To avoid the infinite the iteration, so we also include the new one parameter, so ITR. So if the iteration, it is the more than 1,000 times, so it is also stopped this iteration. Okay, so the last step, so lambda, the eigenvalue, internally, so which we compute the norm, L2 norm of the vector ax, but it's only result in the positive number. As I told you, power method, so we should check the order sign, positive or negative. So if we compute the A transpose AX, so it is also show the the sign of the largest eigenvalue. So we compute this one and so normalize the vector x. Yes, this returns the eigenvalue lambda and the eigenvector corresponding to the eigenvector x. Like this. So internal computation is slightly simple, but as I told you, it needs sometimes it depends on the matrix eigenvalues distribution. So if we have largest and the second largest, they are very close. I think it needs more than 1,000 iteration. But in this case, only 3 by 3 small matrix. So we only have if we comment out this line and then Python over. So we can sorry, this is not they're here. Okay, like that. So initial guess, it is a randomly generated. So every time we see the difference of convergence history. So this time, so the initial guess, it's starting like that. So this is a initial vector x0. Then the computed eigenvalue. So it starts from the 2.49, something like that. Whether it's going to increase, grows to up to the 3.99999. But it includes the numerical error, rounding error. So exact or the strict value should be 4. Yeah. So if you run the different the initial guess using the initial guess, maybe it converges to 4.0. So matrix is the same, but just only so we chose the different initial guess like that. Okay, this is a power method. Okay, so next QR method. So power method only returns the largest eigenvalue. So power method QR iteration. Yep. Oh, you have a question? Okay.
I know that it is a small matrix, so it converges very fast, I guess.
Yeah, yeah.
Isn't like the best practice to let it iterate until a certain tolerance on which the next calculated eigenvalue is under a certain very small number, so you can choose the amount of number after the
yeah.
So I mean, is it the best practice to let it cycle until a certain tolerance is reached?
Yeah. Okay. So power method is a sort of very, very naive sort of algorithm. So internally, we can introduce several tolerance to check the sort of convergence. So just a very simple example. So I use this sample code. Okay, thank you very much. So okay, QR. So this is the next example. Okay, so input matrix. So I chose the sort of this 4x4. It is just it's kind of negative sign, the sort of person operator. So 4x4 person operator. So we can calculate the sort of exact value of the eigenvalue and the sort of eigenvector. Anyway, this is an example, and so okay, so you can see this central part main iteration. So the core part is here. So just QR decomposition. This is provided by the sort of NumPy package. Just only I use this function by calling like this, and we get the sort of result Q and R. So actually, if you compute the Q at R, and then the matrix product, so they are approximately numerically the same as the matrix input matrix A. Okay, so we get Q and R. Or the next step, I update the matrix A by Q transpose and Q transpose from the left hand side and the right hand side matrix Q. To avoid the violation of the symmetric structure, so I put the this third line to keep the symmetry of the matrix. You can easily understand the if operates the matrix from the left to right. So it's quite difficult to keep the symmetry, perfect symmetry. So this additional lines are required. And so X start from the X as a identity matrix, and then multiply the Q from the right hand side. So this converges to the eigenvectors, as I explained, right? So we compute the update of the matrix A and the matrix X. And then, so we need to check the convergence criteria. So it is to be off diagonal. So it is the matrix A should be converged to the diagonal. So off diagonal should be converged to the 0 element. So we checked the maximum number of the off diagonal. So from this find off diagonal function. So this is defined, yes, here. Just we checked the largest element from the off diagonal element. Just return the largest component. Okay, so if this is the smaller than the diagonal components, so diagonal components, the sum of all diagonal elements are mathematically equivalent to the trace function. So compare this trace of the A and largest component, largest number of the off diagonal. If the S is sufficiently the small number, the small enough to check recognize as the convergence, so we stop here like this. Okay, so I try to run this script. Python 3, Python QR iterations. Okay. Okay, we get these results. Okay, so input matrix like this, and D output matrix D includes eigenvalue. So largest 3.6 something, and like that. And then eigenvector. So here, but so eigenvector should be a low vector. So yes, the first element in the this first column. First column from the first row, second row, third row. So this 4 numbers construct the eigen vectors correspond to the first element. In this case, 3.6. Okay, so this is slightly the it depends on column-wise, row-wise, or the data layout. So yeah, it's quite sometimes well in the seeing the vectors product vector structure. So here, don't pick up this one vector from this row, single row or group. So just pick up the first column. Okay, so this is the QR method, QR iteration. Okay, and I think you can check this is correct or not by calling the another algorithm or function. So I prepared built-in eigenvalue helper function ready implement in the NumPy library. So np lin arg I. So this function, so it's automatically selected the internal algorithm. So not only QR method, QR iteration per methods. So in my slide, so there are 3 steps algorithm. So this function automatically selects the appropriate method internally. So this returns as eigenvalue and eigenvector as well. So okay, so we use same matrix as the input. Then Python like Py. That should be the same. No, please wait. Okay. Eigenvalues, so 3.6, 2.6, 0.38, 1.38. Unfortunately, so the NumPy built-in function, helper function, it doesn't return the sort of eigenvalue in a sense of the sort of descending or the ascending order. Okay, so this should be a sort of change, must be the change. Yeah. But so we can compare so the QR iteration and so this result. Oh, yeah. So if you change the sort of the third and the sort of fourth eigenmode, so they are so correct. Yes, this one and this another one. Okay. Yeah.
Is there a reason why they return in order? Like it should be another vector, right?
No idea.
Okay.
Okay, and then so okay, so eigenvector. So if you see the sort of eigenvector, so I think you can see the sort of the difference between these two methods in a sense of the sort of positive and the negative. But we have sort of something freedom to choose the sort of the plus or minus. So if you introduce sort of something a rule to make it sort of eigenvalues as the unique results. So if we start the sort of first element, it should be a sort of a positive number. So we can keep the sort of we can obtain the sort of the same results. But anyway, we can compare the sort of the two different, but internally, I'm not sure which algorithm are taken account in the sort of NumPy helper function. But anyway, we can demonstrate a very small size of the matrix eigenvalue problems by yourself. And then, if you need to solve the sort of large matrix, the large eigenvalue problem, just only sort of modify the sort of matrix structure. So here, now that we have only sort of 4x4 matrix, so add the sort of fifth element, like sorry. Okay, so I increase the sort of 0, 0, 0. Okay, so this is a 5x5 person operator matrix. It's also returned the sort of kind of so the results like this. Oops, I'm sorry. I made a sort of wrong. -1. Oops. Matrix should be a sort of symmetric. Okay, like this. Okay, so the eigenvalue so 3.7, 321.26. Okay, so this is a correct if we choose a sort of 5 by 5, so the person operator matrix. That's case. Okay, so thank you very much. So this is a sort of a very short demonstration. So how you calculate or compute a small eigenvalue problem on the sort of Python environment. If you have any questions, so I stay here. So and I will join the sort of today dinner. Yeah, so please contact me. Okay, thank you very much.